Okay, so now the plan is to talk about two simple theorems. So there's one that's usually called the FourierShift theorem, but it's really the Fourier phase shift theorem. And then the other sort of matching problem is the Fourier frequency shift theorem. And they're similar to each other. And so what we want to do is just go over the Fourier transformation equation. So what does it actually, look like? So what we have for the first one, the Fourier phase shift theorem, is something that affects the phase of our k-space data. So the B0 is an example of something that affects the phase. So if the B0 is set wrong, or for instance, the frequency pre-scan that determined what the resonant frequency of the brain was somehow went bad and set the transmit frequency wrong for what the actual precession frequency is, you're going to get a phase shift. And so if you think of what's going on, so this is image space. So here's a brain and image space. So say we have two stripes, put on the brain. So this is two stripes put on the brain. So we applied a gradient, and that's supposed to have given us two phase stripes. So this is 0, 2 pi. So that's what we wanted. Now, in fact, there was a phase shift. And what caused the phase shift? Well, it could have just been that the B0 was misestimated. So if we misestimate the B0, then what's going to happen? Let's just say the B0 was underestimated, and so the B0 was actually bigger than we were expecting. So what that's going to do is it's going to cause a phase shift. So it'll look something like this. So it's just going to move the stripes. And so the important thing here is we're not talking about a gradient. So this is not talking about a gradient. So anything that affects phase but just to really emphasize it, it's not a gradient. I'll call it a pedestal of phase. So it increments everybody throughout the brain, and it increments, so pedestal of phase, so across space, and also across frequencies, across spatial frequencies, so all parts of k-space. So let's just think about this a little bit. So this was k equals 2, spatial frequency equals 2. But the same thing is going to happen to k equals 3. So that will also be shifted. Notice that the physical shift of the stripes is smaller for higher spatial frequencies, because remember, this is in terms of angle, 0 to 2 pi. And so if we have like a bunch of very narrow stripes, like this, those won't be physically shifted as much. So here's they'll be moved over, but they'll be moved over by, say, this is like a fifth of a cycle. So a fifth of a cycle at a high spatial frequency is a smaller shift than a fifth of a cycle at spatial frequency 2. Doesn't matter. They're all shifted the same amount in phase. So that's what we're talking about. Pedestal of phase that's across space and across spatial frequencies. And so now what we want to figure out is, what does that actually do? What does that actually do to our reconstruction? So what it turns out is that here's our image. So here's our image XY. Or did I just do, no, I just do image X, it's easier. Okay, so we'll just do it in one dimension. So here's image X, and it turns out it introduces a spatial shift. So X0 is a constant. So this guy is a variable, because that's, for each point in the image, this guy is a constant shift. And so the bottom line is, when you mess with the phase, you get a spatial shift. I mean, you can sort of see, you can just see that in this case, that all you've done is you've just moved the stripes relative to the brain. So here's the brain. You just move the stripes over relative to the brain, and so not surprisingly, it's going to sort of like, when we reconstruct it, it's going to shift the brain. But let's just look at it in the Fourier transform equation. So basically, what we're doing here is the reconstruction part of the Fourier transform. So we have the image on the left side, and we have spatial free k-space on the right side, so we operate on k-space to get the image out. So just to sort of make sure that where we are. And so we're summing across all the points in k-space, and all of those points have something done to them. So here's minus I 2 pi kx0. So this is, oh, that's a typo, isn't it? Should be kx there. I've got k0 in my notes. Okay, yeah, so basically so this guy is a constant. This guy's the constant here. So this is the constant shift for each spatial frequency. So that, remember, if we take a complex number, amplitude 1, some angle indicated by this whole mess, what does that do when we multiply something? It just adds to the angle. So this is a way of writing out, we are adding to, when we multiply by that guy, we're adding to this, to the whatever the phase is supposed to be. So here's kx, and then here's our reconstruction. So here's e to the, so there's a plus there because that's the inverse Fourier transform. 2 pi kxx for every spatial x spatial frequency. So what are these things here? So this thing is, this is constant phase pedestal that came from somewhere. We don't know where it came from at all spatial frequencies. So at all spatial frequencies. So there's, because we're summing across kx. And then this thing here is just our signal that we record from the brain. So that somehow got messed up by being multiplied by this constant phase pedestal. And then these are these basically are just the stripes. So, perfect recon stripes. Perfect recon stripes for our inverse Fourier transform. So what this equation says is that if we increment the phase of this signal by multiplying it by this guy, which will essentially add to its angle, when we do this reconstruction, so when we do the reconstruction, this is the normal reconstruction part of the Fourier transform, all we get is an image shift. So you could also sort of look at, so we could take this guy, so another way of writing this is we could write this as, e to the I 2 pi kx, and instead of multiplying this guy, we could just add the exponent. And so you could basically just add the exponent instead. So that would be, so normally it would have been x, but we could just subtract off that x0, and that would make it even simpler. So we could just take this guy and incorporate him into the exponent of this guy. And then you can very clearly see why its image at something equals the Fourier transform at something. So that makes it more apparent, like where does this come from? And all we've done here is we've just kind of fished out the second term in that in the exponent and put it in front, so you could sort of see it as we've actually done a phase shift. So this would be combining both of these into one. So it's kind of like, there's nothing to it. It just says, you add a phase angle to every single spatial frequency, add some phase angle, 45 degrees to every single spatial frequency, do the reconstruction, and what ends up, you end up with a spatial shift. And when you look at it this way, just in real space, so this isn't K-space, this is image space. Image space. You can see what's going on. You just move the stripes. So if you move the stripes over and then you reconstruct, it's not surprising that you caused a shift in the opposite direction. So that's the Fourier phase shift theorem, and that's what causes, this is what causes a B0 defect to cause a shift in the image. So if you have a B0 defect, you'll get a shift in the image, spatial shift in the image. So now, so it turns out that's not the cause of a B0 shift in the image, like when you have say the frontal lobes getting messed up and being stretched out or squished in. You might think this was what's causing it. That's actually not what's causing it. But this is what's causing overall B0 shifts. Like if the shim is a little bit off across the entire brain, it's going to cause a shift upward in the image. Okay, so we'll try to explain what's actually causing those other shifts. But before we do that, we have to talk about the Fourier frequency shift. So frequency shift theorem. And so the other thing that could happen is, what if we mess up where the spatial frequencies are? And so this one is strangely just causes a mess up in the image phase. So here we're again, summing across all spatial frequencies to do our Fourier reconstruction. And here's our image. But we'll just reveal the result at the beginning. Basically, all it does is it just causes a shift kx0. So unfortunately, we've got a subscript on a subscript. So once again, this is a constant frequency. So that's a constant frequency. This is a constant shift in space. So it's a constant frequency, so it's a sort of a fixed amount of frequency offset for all frequencies. And it's multiplied by the image, which will change the phase of the image. And so what does it look like over here on the right side where the error is occurring? So the error is occurring because we thought we were getting spatial frequency blah, like 4, but in fact, what we thought was spatial frequency 4 is spatial frequency 3. Say it's off by 1. So that guy's a constant. This guy's a constant frequency error. And then we are doing, our regular Fourier reconstruction, same as here, I 2 pi k x times x summed across all spatial frequencies. Okay, so this one is the highly strange one. So what does this mean in k-space? So let's just go over to k-space. And so this was image space. Now we're talking about, in this case, I'm talking about k-space. Okay, so k-space here. So what is k-space supposed to look like? Well, if we look at the center of k-space, when you go through the center of k-space, what ought to happen is the echo should be in the center of k-space, like that. You should have a bright spot at the center of k-space, because low spatial frequencies are the most common spatial frequency in the brain. And so the amplitude of the center of k-space should be like that. But what happens if instead of that we got the echo miscentered? So what if the echo actually sort of went over here? So however we miscentered it, like the up gradient, the positive x gradient was a little bit higher than it was supposed to be, and so it moved the echo over. So here's where it should have been. It should have been like over here, but it was off. It got moved. Now, that's a fixed offset in frequency. That's the Fourier frequency shift. So we messed up we put a fixed offset to all spatial frequencies, because here's actual spatial frequency 0, but we called it 4. And here's actual spatial frequency 1, but we called it 5. And here's 2, but we called it 6. So that's what this is. That's what this is. It's a constant frequency error. And what does it do to the image? It does nothing visible to the image. So this one for me was the most counterintuitive one. Like, how could it do nothing to the image? You just completely effed up k-space. You put spatial frequency 0 way off. It seems like it should completely mess up the image, because you completely misidentified, and that's actually spatial frequency 0, but you're calling it 4, and this is, spatial frequency minus 10, but you're calling it minus 7. It seems like that would just like wreak havoc in the image. But it doesn't do anything. What does it do? So this is, this is our freak shifted signal. This is our recon. And this is an image phase shift. Now remember, we're throwing that out typically. We don't even, that's not even visible on the scanner. So what happens when you reconstruct something like this? You can't see anything. So if you do this, you just, you get a brain like that. If you do this, so this is, ft minus 1. So when we do our inverse Fourier transform, what happens to this one? It looks exactly the same. You can't see a difference because if you just look at the amplitude image, remember it's just affecting the phase. It's just affecting the phase. So this is, this is our original image, that we would have gotten if we hadn't had this offset. So this is, image, before phase shift. So that's what we would have gotten if we didn't have this defect here. So here's our defect. At every spatial frequency. So remember, this is like, if this is 3, that means we're off by 3, but we're off by 3 for every single spatial frequency. We're subtracting 3 from every spatial frequency. So all it does is it just messes up the phase. And so if you actually looked at the phase image, so if you look at the amplitude image, it's okay. And that's all you typically look at on the scanner, so you wouldn't even see it. You wouldn't even see it, but what would happen is, if you looked at the phase image, so if I look at the phase image, there's going to be some stripes. And so in order to see that, what you would have to do is save the complex data so that you could actually get the phase image out. And then if you did that, then what you would see is you would see some stripes across the image like this in the phase picture. So you would see these, you wouldn't see it out in space. You would just see this you'd see a little ghostly image of the brain with these little phase stripes in it. And if you look at, you can see some of this, if you look at the cover of Buxton's book, he's got a picture of this. So this would be called, if you're thinking of it in terms of MRI, it would be an echo centering error. So we somehow screwed up the echo and just moved the echo off to the side. So that's the most amazing thing. So if you looked at the whole K-space, what would it look like? It would look like, the center of K-space might be here, like that, and then it would fall off, way off from the place it's supposed to be. And you do a reconstruction, nothing happens. So that's a shocking one to me. So you can get your echo completely off, not a problem. This is sort of why, the Fourier transform is so great, because then, even if you've got your echo completely off, if you get it really far off, if you get it so far off that the echo is not even in K-space, then you start to run into trouble because you completely wiped out your signal. But as long as you're not as long as the echo is somewhere in K-space, then you're okay. Okay, so that's the Fourier phase shift theorem, which says that if we add a pedestal of phase, a constant amount of phase, this guy's a constant. If we add a constant amount of phase to our signal, and then reconstruct it, we end up with a spatial shift. On the other hand, if we add a constant frequency error to our signal, here's the real signal, add a constant frequency error, reconstruct it, we only end up with a phase shift in the image. And the amplitude image will not be changed, because remember, this thing is an amplitude 1 vector with a phase angle, so it's just a pure angle, so it doesn't affect the amplitude component of this. Okay, so that's the Fourier phase shift theorem, Fourier frequency shift theorem. And if you read in sort of an MRI textbook, you'll always go over this. So what causes the B0 defect? So this doesn't cause the B0 defect. What does? So let's erase and try to understand this. So it seems like, so if you know anything about MRI images, especially functional MRI images, you know they've got these shifts in the phase encode direction where there's a B0 defect. And so where is that, where does that occur? And so one place it occurs is where the nasal passages come in. So if you look at your olfactory bulb, the olfactory bulb is part of the brain. It's inside the skull. But then right next to the olfactory bulb is the olfactory epithelium, which is the actual sensory surface that picks up smells. That's not inside the brain, that's outside of the brain. But it's pretty close. So if you look at, so here's your nose, and there's your eye right underneath your temporal lobe. So here's your temporal lobe like that. And then here's your head going around. So the olfactory bulbs come off right here. That's inside the skull. So here I'll draw the skull. So the skull comes around. That's inside the skull. But then right below it, there's a little thin part of the skull. And it's called the cribriform plate. So there's a little very thin part of the skull, and you might have heard, like, don't stick something up your nose. You could go into your brain, and the reason is because this part of the skull is very thin, and here's the olfactory epithelium right below it, and then the olfactory, nerve goes right through that little thin plate. It's also, if you're getting your COVID swab, make sure they don't stick the swab too vertically. It's supposed to go horizontally. Somebody actually managed to sever their olfactory nerve with a COVID swab. So the COVID swab is supposed to go back into here. Like here is a COVID swab. It's supposed to sort of go back into your throat. But some inexpert COVID swab users have managed to sort of put it in like this and actually poke through the cribriform plate. You don't want that. It's supposed to tell the person you're supposed to aim for the ear. That's the proper way to avoid that. But it turns out that was a bit of an aside. It turns out there's some air right there because the olfactory bulb works by getting air up into it. And that air is quite close to the brain. It's the closest air to the brain. And because of that, the B0 field is disturbed there because there's magnetizable stuff on one side and not magnetizable stuff on the other side. And so there's a little divot in the B0 field. So that's one place where there's a lot of distortion. The distortion extends all the way into the thalamus, and it completely sort of messes up orbitofrontal cortex. There's another bit of error right here, which is basically the air inside your ear canal. So if you actually if you take the head apart, you'll see this little tube of bone heading right underneath the brain, the temporal lobe. And so what will happen is you'll get a bad defect right here. So you'll get a bad defect here. It depends on what direction the phasing code is going in, but it can either sort of squash the frontal lobe, or it can move it out like that, and it can sort of mess up the thalamus, which is sort of sitting right behind it right there. And then this one, again, it'll depend on what direction you're doing the phasing code, but it will cause like a little dent here by shifting some of the voxels. So those are, next time I will draw it bigger. So these are B0 sort of B0 defects. So if I draw out a brain here with the thalamus here, you can see what it's going to look like, what the defect is going to do. It's going to like erase like a third of the thalamus, and then maybe cause the front of the temporal lobe to come down like that. I mean, we're talking a pretty big squish. So that's the kind of B0 defect. So what causes those? It turns out it's not the Fourier phase shift theorem. So why not? So, like I said, this was just kind of embarrassing story of how I figured this out. I was trying to sort of eat my own dog food and solve my own MATLAB problems, and I went through the MATLAB problem, and I said nothing happened. So let's just draw out what's going on. So say we stamped on 4. So this is image space. So 4 cycles of K, so K4 in image space. So there's a brain in there. So here's the brain. So remember, it's not K space. It's actual image space. So here's our 4 cycles that we 5 cycles. Okay. 5 cycles. So we wrapped up the spins by a factor of 5. Now, what we're adding to that is a localized, localized B0. So now the idea is plus. So say like somewhere down in this range, so say the B0 is all flat here, and then we've just got a little bit of a divot right here. So right here there's kind of like a little B0 bump. Say it's a positive bump. It could be positive or negative, but say it's a positive bump. So this guy is a localized B0 defect, like you would get from the ear. So this is 5 cycles phase wrap. B4 defect. So what is that going to do? So what that will do is mess up our signal, and so what is that going to do? It's going to distort our stripes, because what it's going to do just in this region, there's going to be a B0 problem, which will cause the spins to precess faster, if they precess faster, they'll get ahead in phase. We're drawing out the phase here. So what does that look like? Well, it looks like we're going to bend this stripe, because right over here they would have been precessing faster, and so they would wrap around like from here to the next time to get to 0 quicker. So, and then the stripes will be okay up here. So the higher stripes will be okay because it's just a localized. So what it's going to do is it's going to stretch out the stripes over here a little bit, and it's going to scrunch them down here because we got a little bit ahead. And that will be, let's put that right over where the temporal lobe is supposed to be. Okay, so here's the looks like a dolphin. Okay. So what is it going to do? In this case, it's going to sort of like cause a little divot in the temporal lobe there. Now that's our data collection. Now we reconstruct it. So now we do recon. So you might think, as I did, well, it's obvious what's going to happen. What's going to happen is you kind of squish that stripe, and if I reconstruct, assuming that the stripe isn't squished, it ought to go up. So, you'd think at first that when you do the reconstruction, that what would happen would be that it would go up, because after all, I mistakenly moved the stripe down, and now I assume I have a straight stripe, but it actually wasn't straight, it was down, and so it should move up. You might think that, but that would be wrong. So why is that wrong? So the reason it's wrong is because you've changed all the spatial. It's wrong if you assume that we changed all the spatial frequencies the same way. So if we assume, we changed all spatial frequencies similarly, so if we assume that we changed them all similarly, what would happen? We would get the Fourier frequency shift theorem. So that's just Fourier frequency shift theorem. And so what would happen? All it would do is that in this part of the brain, it would change the image phase. It wouldn't actually change it spatially. It wouldn't. The spatial amplitude image would be the same. It wouldn't cause a shift. It wouldn't cause a spatial shift. It would just cause a phase shift in the image, but we're throwing that out. So if you try to understand it as just distorting these stripes, if you make the mistaken assumption that we changed all the spatial frequencies similarly, that's not the explanation. So what is the explanation? So the explanation is we don't change all the spatial frequencies similarly because the error is building up. So what's actually going on is that the error is actually sort of building up across k-space. So here's k-space, and so the error is not at the beginning. There's no error, and then or small error, and then as we go up higher and higher in k-space, the error gets worse and worse. So what I'm drawing out here is how much error. And why is it increasing? It's worthwhile saying why it's increasing. It's increasing because the B0 defect has had a longer chance to mess with the phase, because it takes time. This is time going up here. So later in the data collection, there's more time for this B0 to have messed up the phase. So the phase error will increase over time. So now, what does that mean? So if we go back, so what it means, say we have a positive phase error, what that means is, for this part of the brain, we're going to be going to a higher spatial frequency. So remember when we talked about, what if we start off with K-space and we take, say we take 5 samples, in this direction, 5 samples in this direction, and what happens if we now spread out our 5 samples in this direction, but say collecting them the same way that way? That's what we're doing, because what's happening is we've had more time for the error to affect this positive B0 defect to affect our phase. And so as we go up to higher and higher parts of K-space, we're actually sort of stretching K-space. So a B0 defect stretches K-space. But the stretching is caused because of this, how long it takes to collect the data. So if we, for instance, just did a regular scan where we didn't collect all the data in one shot, and we just collected one line at a time, so that there was no increase in B0 caused phase error with time, and everybody had the same B0 phase error like I was illustrating here, then no problem. But because we're collecting the data over time, and higher parts of K-space have more error, that basically is stretching K-space. And what does stretching K-space do? That has the effect of changing the voxel size. So if you start off with voxels like this, when you have a stretched K-space, you're going up to a higher spatial frequency. And so what you'll do is you'll make the pixels, you'll have the field of view if you doubled your K-space, and as a result, you'll make the pixels smaller that way. So you'll actually scrunch the pixels. So basically we stretch K-space, meaning go to higher spatial frequencies, same number of samples to higher spatial frequencies. What does that do? That causes pixels to get smaller, which also means it shifts them. So basically what this will do is, it depends on, what the sign of the error is, and it depends on what direction you went across K-space. Because, you could sort of start from the top and go to the bottom, start from the bottom, go to the top, you'll get the opposite effect. But what it's going to do is it's going to scrunch the pixels just in one part of the brain. So if here's our pixels like this, what it's going to do is it's basically going to effectively just sort of scrunch the pixels like that. And what that will look like is an actual shift, a spatial shift, because you scrunch the pixels. And so what are the, what really causes the B0 defect? So here's the bottom line. So you have a static B0 defect, like the air in the nasal passages. And then successive increases in phase error. For successive spatial frequencies. That's the important part. And then third, small size phase encode blips, because the same thing applies to the frequency encode, but the gradients are so big relative to the B0 defects that it's less of a problem. Small size phase encode blips. So that's why it only occurs, this is why it only occurs, phase encode only. And so basically you need all these three things to come together. So you have static B0 defect, and then when you're collecting your data, the error is spatial frequency dependent. It's worse for higher spatial frequencies, also known as stretching k-space, just for this guy, right? So the rest of k-space is okay. So that's the part that's a little counterintuitive. We just stretched k-space for like around the nose, but the other part of k-space space was okay. And so when we reconstruct, we end up with the spatial shift. So that spatial shift is actually it's not directly the same kind of pedestal of phase added to all spatial frequencies so that we cause a spatial shift in the image. It's not a case of that. It's more a case of if we actually added the phase offset to all the different spatial frequencies, we're actually shifting our frequency. And so if you collected the data all at the same time and there wasn't this incremental increase in error, you would just have a frequency shift, and a frequency shift would be invisible. So that's so like I said, for many years I didn't understand this properly, what it was actually coming from, but this is the real reason for it. So it's a static B0 defect, but successive increase in phase error because the B0 has had longer to mess up the spins for successive spatial frequencies, and that leads to a stretch. K-space stretches, and when K-space stretches, that means that the pixels get smaller, and so you squish your image, but it only occurs in the phase encode direction because the readout gradients are so big relative to the B0 defect that there's much less of an effect than there is for these tiny little blips. Okay, so there's various ways to try to fix this. So one of the typical ways you might want to do is like go up in one scan and then go down in another scan, because that will reverse the direction of the squishing. If you go up, you'll get stretching in some places and squishing in the others. If you go down, those will all reverse. Wherever it was stretched will now be squished. So you could try to record even higher spatial frequencies on purpose, so that you could have the information to unoverlap these things. So one of the problems that occurs is the stretching can be so severe that it can effectively pile up multiple voxels. So like this voxel here, might get information from this guy, but also information from this guy, and maybe even also information from this guy. They'll all pile on top of each other. And if they all pile on top of each other, then it's going to be harder to, so you'll get one really bright voxel. You'll notice wherever there's a B0 defect, there'll be bright voxels. Why are they bright? Well, they're bright because basically some data from another place got piled on top. And so in that case, you've kind of lost information, because you've got one bright voxel, but you don't know how much of that voxel goes back here, and how much of it goes here, and how much of it goes here. So that can be an issue even if you go up and down. If you go up, one advantage if you go up and down, what's going to happen is you'll get voxels really piled on top of each other, but going the other way, you'll stretch them apart. And so then you can actually see them individually. And so that's sort of phase up, phase down method of trying to fix this. So, but the fundamental basis of it is this successively building error, which has a result of stretching k-space, which has a result of squishing the effective voxels and causing a spatial shift. Okay, well, end the recording there and try to get some questions.